Warm greetings from the Garden City of India, Bangalore. The subject is sensitive in nature, and to be safe legally, I have avoided using classified pictures for my presentation. All my pictures are generally found in the open source. For obvious reasons, I will be using only those pictures. The rest you can imagine. Electronics in the battlefield is the topic I shall handle, and I hope I will be able to do justice to this. The battlefield is like the slide you see. It's quite populated, it's dense. There are a lot of platforms, weapons, a lot of human effort behind it, and is also swarming with a lot of people. Before I kickstart the talk, I would like to make a dedication. I would like to dedicate my talk to the unsung hero of our country, both civil and military. On the civil, particularly the corona warriors who are working untiringly to control the situation, and all those civilian, ordinary Indians who have made an impact, who have made a difference to the quality of life for all of us and for the country at large, but are not celebrated, not as recognized, but they keep doing their job without any expectation of returns. Coming to the military, there are a lot of unknown heroes who are not celebrated. The dedication also goes to them. And lastly, Dr. APJ Abdul Kalam, the man who taught us to dream big, who inspired the young and the old to dream and cherish their dreams, chase their dreams until the last breath. So my dedication to all these people. With that, let me commence. Battlefield electronics, I would like to cover my topic today, stepping through the historical perspective, the national security considerations as primer for the meat of the matter, which I would like to discuss. Then we switch on to what is called network-centric warfare, NCW, because we shall do a top-down approach to the subject. We shall see some glimpses of land, naval, and air assets, a flight through avionics. Avionics stands for aviation electronics, as all of you know. Let us look at some requirements of the military electronics, enabling technologies which go into the realization of these systems and capabilities, certain standards and regulatory bodies in India you should be aware of, and a look into the future before I conclude. Let me admit that the scope of the subject is such that, if you permit me, I would like to spend one full week with all of you, and still I may not be satisfied. That is the kind of bandwidth of this topic. You can pick up a one system or a subsystem and do your MTech and PhD, and still you may not be satisfied, and there may still be things to be explored, and that is the kind of scope and depth of this subject. So let's admit that it is a huge topic, but let's see how much justice we can do in the limited time that we have. We have about 1 hour and 40 minutes to go. As we cover the topic, you may think of areas of specialization you may be interested in as you get familiar with this subject a little more than you have already. Make in India is a phenomenon that has been happening ever since independence in 1947, but of late, it has become a priority of the country, both politically and industrially. And as Dr. Arun brought out, you will see the country making rapid strides in this domain in the days to come. And you are passing out of the university at the right time, I must say. And you must have observed that, of late, the government of India even declared an import embargo on a list of 101 items of defense weapons and platforms. This also means that from the time that is December this year to December 2024, all these embargo weapons and systems will have to be produced or co-produced on Indian soil. And that means a lot of opportunity for us engineers. The growth of Indian industry is going to witness rapid strides, as I already brought out. You can pick and choose certain career options from this domain, open to you. And I must admit that To be associated with military electronics, you need a different kind of motivation. And the motivation can always come to an Indian citizen or any citizen for that matter from the historical perspective that we share in common. Let me take you through a few discussions. At the outset, some of you may think, why do we need armed forces? Because there is huge money spent on having a standing army, equipping them, training them, feeding them. And if all that money can be saved, it can be put into the infrastructural development of the country. We can make roads, more buildings, more hospitals. We can educate, spend more money on education and general welfare. The answer to this question lies in the history of mankind. I know it is voluminous to read the books on World War I and World War II, but since you are all tech-savvy people, if you can subscribe to Netflix, there are documentaries which are much shorter in nature, but will give you enough in-depth insight into why the people get into wars, why wars have been waged between countries, between clans, between races, and what is there inside the human psyche when it comes to relationships, whether it is regional or continental or across ideologies. You may also like to briefly go through the Arab-Israeli conflicts. Why I'm recommending this is, if you watch some documentaries on Arab-Israeli conflicts, you will be more convinced about what I'm speaking now, that it is the electronics and the quality and efficacy of the electronics that decides victory in war. I'm not saying that the electronics alone will win you the war, but it has got a large say, much larger than we normally think. All the Arab-Israeli conflicts are proof of that. A country like Israel, which is probably of the size of Kerala, was able to hold on to 6 attacking nations simultaneously at the same time and still win the war only because of technological superiority, and they had much more powerful electronics, electronic warfare equipment, some of which we will visit. These are some topics we shall visit today. Coming to the Indian scenario, you know from the history that we have already waged a few wars. These are full-scale wars which we have waged: 1962 with China, 1965 and 1971 with Pakistan. We have also waged limited wars, Kashmir in 1948, wherein we lost POK. IPKF operations in Sri Lanka. If we had not gone into Sri Lanka, probably China or Pakistan would have occupied, and it would have opened a new war front for us. So we had to go in. Just about the time some of you were born, we had the Kargil conflict. Then we have what we call LICO, low intensity conflict operations, continuously happening in the state of J&K, Assam, separatist movements in Nagaland, Naxalite operations about which you keep reading news. All these are our historical perspective. Going on, we have a line of control with Pakistan. We have a line of actual control with China. We are familiar with the expansionist policies of China. If you are not very clear, please Google, or you can go to, keen for the history of China. If you can visit last 2000 years of Chinese history, or at least from the regime of Ming dynasty, you will appreciate why China is doing what it is doing. Why does China think that Hong Kong, Taiwan, Singapore, Arunachal Pradesh, Sikkim, and all belong to China or should belong to China? It is important to understand this. You may have, please, your own views about this. And we should also be conversant with the current standoff with China. You have been reading news on what is happening in East Ladakh. Pangong Tso Lake, there is a picture I posted here. This is the scenic, beautiful Pangong Tso Lake, and you can see some stones raised there. This is the place, one of the places where the Chinese troops and the Indian troops fought hand to hand without weapons, because this is a demilitarized area and you cannot use weapons there. And Galwan Valley has been in and out of the news. And if you have read the news today, Vietnam has reported to India that there is military activity, combat aircraft operating in South China Sea. That brings us to the national security considerations before we start the core discussions. You can see it on the map. We have a western border with Pakistan. We have northeastern border with China, longest border with them. We also have border with Nepal, Bangladesh, Myanmar, and Bhutan. And we also know that Nepal, though, has been very friendly with us of late. It has been distancing themselves from us, particularly after India probably failed to an extent to rebuild Nepal after the earthquake, and the Chinese stepped in. If you go to Kathmandu, Pokhara and all, you will see a lot of Chinese presence there rebuilding the nation. Naturally, they tend to drift towards China. Bangladesh, though the people who know the history are grateful to us, it is a matter of time before we can have ideological differences because it is an Islamic nation and it is not a secular country like India. Bhutan has been probably neutral. Myanmar, we have a problem of Rohingya influx from Myanmar. So it is up to the diplomatic efforts of the country to see how we settle things with Myanmar. Our look-east policy needs a review. We all know that. We have 65,000 square kilometers of sea control to do, a huge task for the Navy and the Coast Guard. We have growing presence in South China Sea and Coco Islands, particularly by the Chinese presence. And we have a wavering Sri Lanka, which is economically going weak. They have been offering more and more infrastructural projects to China at huge loans. And we probably know that, okay, there is a Chinese trap in all the developmental projects which China is undertaking, be it in Sri Lanka or in Pakistan. Homeland security, there are concerns. We know the separatism, Naxalism, which is rampant. So looking at all these in total, you will agree with me that we have a requirement, we need to brace for the challenges. Whether the problems are internal or external, we need to brace, because should there be a war, in war, there is no prize for the runner-up. So we need to be there, ready, capable, and constantly vigilant and improving. I suppose this should be enough motivation for you, all of you, to be with me through the rest of the discussions today. We go on to the running modules, the core discussions. We start with network-centric warfare. I shall touch upon the genesis of network-centric operations. I am saying operations because the moment there is a civilian component in the net-centric activities, I must call it NCO, net-centric operations. We shall see a couple of examples and look at the components. And that slowly we'll get into the engineering aspects of all these topics. Coming to the genesis, we all know how conventional battles were fought in the Stone Age. People fought with stones, then they developed weapons, spears, and then went on. And there was also an era when battles were fought on designated places, like the battles you see from the epics of Mahabharata, Ramayana, or even some of the historical wars elsewhere. The bugler plays the bugle in the morning and the battle starts. In the evening, bugle is played and they stop the battle. Then they take rest during the night, and they start again. There was an era when wars were fought like that also. Then came federated wars, the purpose of which was to occupy territory. So initially it must have been a single point entry. Then there were federated wars, that means attacking an area on multiple fronts, which often led to what is called fratricide. Fratricide is when you kill your fellow soldier by mistake. Fratricide happens, it's a reality of life. Fratricides happened even during the Gulf War when the Allied forces came in. And between the UK forces and the US, which were fighting together against the Iraqi forces, there were cases of fratricide, so some of you must have read somewhere. There are also cases of underkills and overkills if the men, material, and rations are not managed properly, judiciously. That reminds me of one incident I must mention. If you listen to Dr. Shashi Tharoor, He's available on YouTube. This particular speech is available. His speech about what the British did to India. During the Second World War, Bengal was facing famine. A lot of people were dying of shortage of food, and there were shipments headed for Calcutta, which was meant for feeding these people who were starving. Winston Churchill decides to divert these rations for the troops who were fighting elsewhere in the Middle East and towards Europe. The British leadership in India kept pleading with him to divert the food to Calcutta, otherwise people would die. His response was, "Why is Gandhi not dead yet?" And he diverted the rations that went somewhere else. And later, it was known, it is recorded in the history that all the rations which arrived were surplus to requirement for the troops there, while 35 lakh Bengalis died of starvation in India. So similar things, that is a civilian example, but similar things can happen during war effort also, underkills and overkills, if these are not managed properly. That is men, material, rations, and all the supplies. So logistics is a very important component of war effort. There is the need for coordination is of a very high degree. So all these requirements, together with the real-time operational control, gave birth to what is called network-centric warfare, NCW. Let us see a civilian example for your appreciation before we get into the military scenario. Suppose you are posted as an engineer, part of the think tank, to implement a traffic management system, say in Palai or Kottayam or Cochin, or the state at large. You will think of a few things: cameras at all vantage points. You may put embedded acoustic sensors at crossroads. There is a traffic junction shown in the picture, so that automatically the system can calculate the number of vehicles approaching from each road to dynamically decide for how long which light should go green or red. Unlike it is pre-timed. Most of the traffic lights are pre-timed. Here you can have an intelligent traffic light system giving you real-time control, equivalent of a policeman who looks at the traffic and decides how much for how long you should open. You can have policemen with instrumented policemen who may have mounted camera or sensors, which will also relay information to the data center. You can have patrols reporting to the data center. If required, you can have helicopters airborne to take videos or still shots of a scenario where there is a crisis. So all this put together is called the sensor grid, which forms part of a network-centric system. There is a sensor grid. Now we have what is called the C2 grid, that is command and control grid, where all the data, the huge data that comes in, are processed systematically. You have a control room where all the decisions can be taken and real-time monitoring is possible, like you may have observed in movies. And to run this efficiently, you need to develop state-of-the-art, intelligent, powerful applications. And if you have a link with the National Informatics Center, you can even pull data in real time. Suppose you have picked up a vehicle with a particular registration number. Instantly, you can come to know who is the owner of this vehicle. And the rest of the actions can start. So this is C2 grid. Coming to the action grid, one result of having all these sensors and management is, okay, you have intelligent traffic lights, which will ease the traffic jam to the least possible. You can automatically penalize offenders. Kerala is an example. I myself have paid penalties for mistakes I have made. You can automatically launch air ambulances if there is a traffic accident, and the system can be very efficient because it's automatically flagged. You can even have airborne quick reaction team who can be offloaded at the site for relief operations. So look at the beauty if you have net-centric system, even for application or management of traffic. So this is the concept, and I'm sure you appreciate this. So coming to a national level where NCO comes into play, integrated defense operations is easily understood. I have already covered. We also have situations where we have to manage disasters. It may be natural calamities, there may be floods like the one we had in 2018 in Kerala, during which I was in Delhi. I was part of the coordination team which was managing and coordinating assistance from center, and I was also in the team which used to brief the Home Minister and the Defense Minister on a daily basis as to how the operations are going on in Kerala. That is the flood relief work by Army, Navy, Air Force, Coast Guard, and NDMA, National Disaster Management Authority, the state authority, the coordination of the relief supplies which were sponsored by very generous states like Punjab, Karnataka, Andhra Pradesh. They kept giving lakhs of food packets, and they were to be airdropped or landed in various points in Kerala. So real-time coordination of all these is a result of an NCO capability. During civil disobedience, also NCO comes into play. If there is a civil war, of course, the administration and all our national resources come into play, thanks to the NCO. The air and rail bookings, banking operations also have a network behind it. And we also have National Informatics Center-based services like Passport, Aadhaar, and so on. And you see two pictures here. I would like to mention the name of a gentleman, my friend, now Air Commodore Krishna Kumar. We call him KK. He was in the picture you see here, helicopter lifting a person from the sea, and while two more people are waiting. And here you see another aircraft in which some people have been picked up. This is an N-32, a transport aircraft, and you can see an Air Force person signaling before the aircraft is leaving for its destination. You know, 2004, 26 December, tsunami hit the Andaman Nicobar Islands. This picture is symbolic. And KK was a wing commander then. He ran to his helicopter to kickstart his relief operations. And for next 2.5 days, he kept flying over the sea, picking up people. He picked up more than 300 people who were still floating or were able to remain afloat in the sea. And he discontinued his efforts only after he was sure that there are no more people alive in the sea and waiting for pickup. These are some glimpses of relief operations from my collection. This is a fellow officer of mine. Okay, now let's come to the brass tacks. Electronics starts from here, my dear audience. To have an NCW backbone pan-India, we need to have the kind of a backbone connectivity. There are thousands of kilometers of fiber optic cable laid pan-India by BSNL, not only for military operations or civilian operations. It's a multi-purpose thing. BSNL's own services run on this. A lot of cellular operators hire pairs from this, and they are making use of this NCW backbone. So what I want to say here is that it is not only for military purposes, but is also for civilian and other applications. This particular network exists. And as we know, we have islands to be covered, the Lakshadweep Islands on the left side and the Andaman Nicobar Islands on the right side. Those places are covered by satellites, and also there are reaches in northern regions of India where laying of cable is not feasible. Those places have been linked with microwave links. And we also have a submarine cable project coming up, which will run from Chennai all the way to Port Blair, that is 950 kilometers away. So through the sea, it would be more than 1,000 kilometers. Here you can see a picture of how the submarine cable would look. So this backbone is also coming up. Until then, we are on satellite connectivity with Andaman and Lakshadweep. So that is the backbone that we have for NCW. Then we have NCW components. The pictures are self-explanatory. We will look at the list. Backbone connectivity we have already seen. It is pan-India and pan-area. So depth of penetration is sufficient for meeting all our objectives. The media used are fiber, copper, Ethernet, satellite, and radio links. Network devices We will see in the subsequent slide. The grids of operations you understand already now, because we have already seen how the sensors form a grid for an NCW. Then we have the engagement grid, which is also known as C2, command and control grid. Then we have all the engagement grids. That means the action people are called the engagement grid. Going to the next slide. We need huge data centers because there are the size of data that is to be handled is voluminous and it's mind-boggling. So we have data centers strategically located. Then we have synchronous transfer modules known as STM1 to STM4. These are equipment which can push gigabytes of data per second. So the level of these equipment is decided based on the architecture. Coming closer to the area of operation, we have L3 and L2 switches. Some of you who are already into network engineering will be familiar, or if you happen to work in this area, you will get familiar with these systems. Since all this information has to be classified, they are secret, we don't want unnecessary people to know this, and everything is on a need-to-know basis. We have to have bulk encryption units in place. We also need intrusion prevention systems. They are systems by themselves. We need IP encryptors at the terminal ends, and of course, terminal end secrecy devices. It's a collective term. The device may vary from application to application. Going on, at the user stations, we may have IP phones, Internet Protocol phones, which can be used not only for voice, we can also do video talk on this. And there is a need for data warehousing at the local level, email services, a whole lot of web services, chat, applications. The applications you are going to run on this backbone depends on all the utilities you want to run. So there are applications and application of applications, layers of applications. It's a mind-boggling subject by itself. Some of you who go into network engineering or switch to firmware and software as your profession would end up spending your life and time and energy in applications. We have already seen the grids of NCO. Let us look at it systematically once again. So primarily there are three grids: sensor grid, which is used for targeting and feedback when it comes to combat operations, war-making effort. Then we have the engagement grid where all the war-making machinery is employed. And behind that, we have the command and control grid. And between these three, there are a lot of informations that flow: integration of systems, decision-making, logistic effort, and needless to say, trained people who know their job and constantly improving their skills behind this effort. Let's get into pictures, which will be more self-explanatory. Coming to the sensor grid, this is what you will see if you have an infrared line scanner or infrared device, which is day and night capable. This is an infrared camera mounted on an unmanned aircraft or helicopters as the need be. These are combat vehicles with a whole lot of sensors. You can see some of them are in the laser range, some are in infrared range, some are in ultraviolet bandwidth. We will visit those topics later. This is a sensor which can be buried underground. The smaller versions of these are what are used in the traffic management systems. Here you see huge radars. This is a constellation of satellites watching over the Earth pictorially. This is what is called an aerostat. Right now it is on ground. It is a station by itself. It has got a host of sensors, and these can be launched into the sky. They typically go up to 500 or a little more of height. Thanks to the height, they can look deep into enemy territory. We call them aerostats. This is a picture of an unmanned combat aircraft. What UCAVs can do, there is a way to enjoy and educate yourself. There is a movie I would like to recommend. Please watch Eye in the Sky if you can, and it will give you a lot of insight into how the Americans have been targeting terrorists in Afghanistan and Pakistan, and they continue to do. And what we have and what we do is not a point of discussion, because I told you we will only have open source discussions today. Coming to an individual level, Here is a commando who is instrumented, and there is a host of sensors on his body. Some of you were probably excited or curious to know how a commando mission went to all the way from US to Abbottabad in Pakistan to terminate Osama bin Laden. There is a movie on that topic. There are books on this. And I must tell you that when people go for such commando operations, they get clothed like this. He's wearing a lot of sensors, not only the human beings, the commandos who go, even the commando dogs who go and parachute along with the soldiers from aircraft onto the ground are instrumented, and these commando dogs come very handy in such operations. So they all form part of the sensor grid. Going on, some more pictures of sensor grid, cameras. This is what you see if you have a night-capable infrared or night vision goggle. So soldier hiding and waiting. This is another camera that is mounted. What you see here is the PPI of a radar. This is a surveillance radar, probably able to look 600 miles or 800 kilometers, more than that, into the enemy territory. This is an unmanned aircraft being launched. Another one here, satellite in the space, an aerostat, a vehicle-mounted sensor system, and here you can see a transport aircraft dropping a sensor. Going on, command and control. As you would already appreciate that this is a place where the big data is handled, the data fusion takes place, and all the latest innovative ideas or what is being professed, taught, or even conceptualized are put into action here. Machine learning, artificial intelligence, all this is pumped into the activities. Host of applications, they are the game changers, but having information is one thing, but using them in real time for real-time employment is another game. That is where the applications come in. The degree of automation does not need any further statement, and there is a lot of real-time brain functions that happen. This goes to say that, okay, the men behind the machines are as important as the machines, or maybe more important. Going on, coming to the actor grid, the pictures are self-explanatory. On the land, we have tanks and armored fighting vehicles. We have soldiers equipped. We have anti-aircraft artillery systems. Going on to the sea, we have warships, carrier ship, submarines, anti-aircraft missiles, aircraft of various kinds, attack helicopters. And here you can see a picture where the paratroopers, commandos are moved by helicopters. This picture is taken in the Northeast, a beautiful place. And if there is favorable air situation, we will even use transport aircraft to drop bombs. Here you can see an N-32, a transport aircraft dropping bombs. Continue with action grid. Here, even a soldier on foot can have a weapon where there will be electronics inside, because a sniper's gun also has some electronics into it. And obviously, UCAVs will have, all the modern aircraft will have. And this is an anti-ship missile being fired. And this is a picture of an array of battle tanks in action. So that's all about action grid, pictorial, some pictures for treat for your eyes. Let's now come down to the discussion on electronics. Here you can see a soldier launching a drone. He's not launching a drone for fun. The drone is going to carry something on board. It may be a camera which will telemeter some pictures, videos in real time, or still photos, or pick up some transmissions which will be relayed back to the ground, or you may come back with a recording of all that it has picked up. So these informations go into the war-making effort. Here you see an all-in-one vehicle. This is a search radar which searches for the airspace which is supposed to be defending. And this is another radar, which is a tracking radar, which will track the aircraft or vehicle at which you have to fire the missile. And these are the canisters from which the missiles will go. So it's an all-in-one station. We call it a firing unit altogether. And about a man on ground, I have already covered. So the content, the degree of difficulty or the degree of sophistication of electronics in all these systems will vary from system to system. Here you see a carrier ship being escorted by warships. There are aircraft on board this carrier, and a closer look at such ships, the Ganga Kaveri class of ships which we have in the Navy. This is one of the pictures, which is the open source. You can see the host of systems. This is a radar, this is another radar. These are all radomes and antennas of various systems. And what is there in these canisters are, torpedoes and missiles, which will be. This is also canisters in which anti-aircraft or anti-ship torpedoes and missiles are housed. So you can imagine the quantity of electronics behind all this. Air assets, there may be a repeat of some of the pictures for your treat. This is a Mi-35 helicopter. This is AVIONICS aircraft. And this is the heavy lifter of Indian Air Force. This is Mi-26. It can pick up 16 tons cargo inside, Su-30. Okay, so that was all about, overview, a bird's eye view of the weaponry, the range of systems that we need to look at. Now, you will agree with me if I say that the degree and content of electronics goes exponentially high when we move from a battle tank or an armored fighting vehicle to ships to aircraft. So I thought the best way to bring you at par is to spend some time on avionics. We cannot jump to avionics without appreciating the history of flight in a nutshell. So here you have the picture of Kitty Hawk, the first man-made aircraft that flew, flown by Wright brothers way back in 1903. And in 107 years, how far we have come. This is a biplane which was used during World War II, Tiger Moth. And this is the cockpit of Tiger Moth. Probably there is no electronics here. They are all instruments which directly read the airflow from the air pressure, or maybe simple electromechanical devices, or they were rather electrical systems than electronic systems. Then came the 70s, late 60s and 70s, where this is the cockpit of a MiG-27, MiG-23. There is much more electronics than the Tiger Moth and the Second World War aircraft. And here at the bottom, we have the most modern. This is the Airbus class of aircraft, which is full of electronics, both in the cockpit and all over the aircraft, you can imagine. This is a C-17, American make, but used by Indian Air Force now. And this is the cockpit. So that's about the exponential growth of electronics in an aircraft, from zero electronics to mostly electronics. And I must say here, the cost of electronics on board an aircraft today, depending on the role of the aircraft, may vary from 20% to over 75%. In an AVIONICS aircraft, the cost of electronics is much more than the cost of the aircraft or the airframe and the engines put together. So that is the kind of scope of electronics today. When we say avionics, which stands for aviation electronics, primarily there are two classes when we classify. One is the mission avionics. That means all the electronics which go into making an aircraft fly safely with all its onboard navigational system, communication systems, its ability to navigate safely from one point to another, and safe takeoff, safe cruise, and safe landing. So all these systems which aid this goes into what is called mission avionics. And there is another class, electronic warfare systems, which give the military aircraft an edge when it comes to war-making efforts. So the weaponry also I'm putting under this blanket. Coming to commercial avionics, the aircraft which you will fly routinely, whether you take Indigo or fly Air India or Vistara, let us see what are the systems which are commonly there in all these aircraft. You have a weather radar for the pilot to know whether it is safe to fly through the clouds he sees in front. He is supposed to avoid CD clouds, cumulonimbus clouds, because the aircraft can get electrocuted and aircraft can disintegrate if you enter CD clouds. So the aim is to be safe as far as flight is concerned. So you have weather radar for that. We have flight management system, which takes care of A to Z, from the start to the landing, all the activities that take place. It helps the pilot, fly the aircraft safely. Navigation, air data system, flight data recorder, which comes handy in case of an investigation into an incident or an accident. For example, the Calicut accident, which is obviously the investigation, the primary tool for investigation would be the flight data recorder. There is a system called autopilot, which pilot can engage after he gets airborne. So the autopilot can bring the pilot close to the airfield where he has to land, and then the landing can be done by pilot himself with the aid of some more systems, which obviously today we don't have the time to get into all those because we need to quickly come to the military electronics. There is something called fly-by-wire, which is a technology. It is very interesting. I shall spend 5 to 10 minutes on that after this. We have VHF omnidirectional ranging system to tell the pilot how many kilometers the destination is and it is in which direction. Instrument landing system, calibration Mark 1, 2, there are different degrees. If you have a Cat 2 ILS calibrated, the ILS system can land the aircraft. And that is used by the pilots if he has the category to do that when he lands in airfields which is very densely fogged, and then visibility is, say, in feet or a few meters. Otherwise, typically what happens is he uses ILS to make the approach. He comes close to the runway, and the last few meters of flying, or say 10 meters of height or so, he does visually, he touches down. But ILS can actually land the aircraft if you trust it. We have what we call radio altimeter for very, very accurate height measurement from the ground. Host of communication systems. We shall visit communication systems in subsequent slides. And we have flight deck instrumentation. You saw the picture just now. And lastly, which is typical to commercial aircraft, is the infotainment, information and entertainment to keep you engaged. You can watch movies, listen to music, and or now that aircrafts are now providing satellite links, you can even browse WhatsApp, and you can keep to it, you can switch to Twitter or Facebook or whatsoever you want to do, even during flight. Coming to military avionics, mission avionics is common. You need mission avionics to fly the aircraft. What you see in the picture is a Mirage 2000 with its some of its armament. This is the flight in which I have served for 7 years. Flight management system is very much there. We also have a fire control radar in the place of a weather radar, because we use this radar also for, besides weather radar duties, we also use it for aiming and firing our weapons. We have a weapon management system so that we can manage rockets, missiles, bombs, laser guided bombs, and also some more, probably classified system, which I'm not talking about here. And then comes the electronic warfare systems, which is a huge decider when it comes to war-making effort. My reference to Arab-Israeli conflicts refers. You can visit that for you to get convinced. And let us visit fly-by-wire, since I talked about fly-by-wire. You must have heard this term here and there, and after today, you will have clarity about what is this, and you probably will be able to even talk about fly-by-wire as a subject. Fly-by-wire is also known as EFCS, Electrical Flight Control System. An aircraft which has got fly-by-wire like Mirage 2000, Su-30, and all the latest transport aircraft, they have no mechanical linkages from the joystick which the pilot has in the cockpit to the control surfaces which move for making the aircraft climb up or go down or turn or make maneuvers. This means that the weight of the aircraft can be hugely reduced because there are no mechanical linkages, and also failures because of a break in the linkages, wear and tear, all that is avoided. So it is like flying an electronic aircraft. So that is fly-by-wire. Going on, control surface commands are picked up by electrical sensors. Now that we are very conversant with the sensor grid, you can appreciate if you have all the right sensors in the right place, what the pilot wants to do can be picked up by the sensors, and they can be fed to the command and control center, which is known as the EFCS computers in our language, or we call them mission computers, and it is processed out there. Then we have what we call servo actuators, because to move the control surfaces at that speed, you need a lot of power, you need torque, you need muscle power. And it is not going to be possible for small sensors to do that. So we have servo actuators, which are powered by hydraulic power, but then it is moved electrically. We will see that. The controls are electrical, but they are hydraulically powered. So all these things put together constitutes the fly-by-wire. Let us understand this at a macro level. The pilot's orders, his wishes, which he expresses by moving his joystick or some control switches, are picked up by the electrical sensors. They are put to the data computer, and the electrical signals go to the servo actuators, which move the control surfaces, whether it is radar or flaps. If you get into basic aerodynamics, you will understand all this. And then there is a feedback that comes back to the computer to tell how much movement has taken place. So then he does some automatic regulation. You can see a control loop here in which pilot is not in the loop. That means pilot expresses his wish, and the system does what he has expressed. And there are a lot of automatic corrections and things that happen. You will understand a few of them later. Coming to the redundancy organization, meaning there should be no way fly-by-wire can fail, leading to a catastrophic incident. The aircraft can come crashing down like a coconut if a fly-by-wire fails. We know that. It should never happen in the history of the service of the fly-by-wire system. So there are enough redundancies, and the probability of total failure is something like 10 raised to minus 12. So you can go back and calculate what does it mean. So we have multiple sensors for each pickup, each sense, and then there is a voting circuit. So the average value comes out as the sensor output. So by having this redundancy, we ensure that there is no chance of total failure of any sensory system. This is one of the pictures of such sensors. This is the lever you can see. If you give a movement to the lever, electrical signals come out of this. And this is a 4-track sensor. These are artificial field units. You need to know, now that the pilot has got only electrical controls, his joystick can be moved very easily. So he should not touch that by mistake, which will result in the aircraft moving violently. So he has to feel the flying, for which artificial field units are given. So he has to deliberately make a movement with certain force so that the aircraft behaves. So it is not that you tap the joystick with your finger and the aircraft will jerk. No, it doesn't happen. So it has to be sensitive enough, but not extra sensitive. So artificial field units come into play for this. So they go part of, since you have studied the controls system, open loop and closed loop control system, I want you to appreciate, in a conventional aircraft, the pilot is at the center of all activities. He has to perceive the environment by looking outside, by feeling the seat of pants, and looking at the instruments. He has to make all the decisions himself. He has to fly the aircraft and take the feedback visually and otherwise, and then make all the real-time decisions. Thereby, the pilot workload is constant, and he has to work tirelessly from takeoff to landing. And it can be quite cumbersome and tiring in case the flying is for many hours together. So this is an open loop control system where a typical conventional aircraft is flown. Coming to EFCS or fly-by-wire aircraft, pilot is out of the loop. So that he can concentrate on operational availability, his purpose of his mission, weapon management, what he's actually looking for during the flying, and for the mission objectives, he can set aside time and energy, while most of the flying can be taken care of by the fly-by-wire. He only has to intervene whenever he wants to make a change. Let us go on to appreciate this system or a concept a little more. In an aircraft, there is something called center of gravity. Anything has a CG, you are familiar. When it comes to aerodynamics, there is something called center of pressure. When the CP and CG coincide, the aircraft is perfectly balanced. So in a fly-by-wire aircraft, we deliberately keep the CP forward and the CG behind. That makes the aircraft unstable. And then we make it stable by the capabilities of the fly-by-wire. So the takeaway is the aircraft is fundamentally unstable but made stable by fly-by-wire. So the aircraft can be made much more agile. It can fly like a bird and maneuver like a bird. That is the beauty of a fly-by-wire aircraft as compared to an aircraft which is conventional in nature. Then there is something called variable gain. You will appreciate that the air is very thick, much denser at lower altitudes. And as you climb, air becomes thinner and thinner. So the amount of movement you have to give to the control surfaces of the aircraft varies with altitude. This variation is taken care of by fly-by-wire. Pilot has to give the same movement for his desired results, irrespective of altitude and thickness of the air. That is left to the EFCS computer to worry. This is called variable gain. This is an automatic function of fly-by-wire. Stabilization of an unstable aircraft, I have already mentioned. So you make it fundamentally unstable and fundamental stability by fly-by-wire. And the aircraft is made much more agile by doing this. There is something called asymmetric configuration. Look at this picture. You can see there are 9 hardpoints or 9 stations where missiles, bombs, or drop tanks are fitted. Imagine a situation where bombs are dropped from only one side. That means all the stores under one wing is all dropped. What will happen? The aircraft will tend to roll because of the weight on the other side. The aircraft will become unstable. Not in the case of a fly-by-wire aircraft. This asymmetry is automatically picked up by the fly-by-wire system, and the aircraft will continue to fly steady and straight while the pilot does his rest of his weapon management. So this is the beauty of a fly-by-wire. Another beauty of fly-by-wire, redundancy I have already covered. The probability of total failure I have already mentioned to you. So this is another picture to appreciate the asymmetric configuration I was talking about. Suppose you are carrying bombs and rockets on one side, and you expend all these stores on one side. In a Mirage 2000, Mirage can carry 6.5 tons externally. So suppose you have offloaded 3 tons on one side and you have all the 3 tons on the other side still remaining. The aircraft will still fly straight, which is not humanly possible in a conventional aircraft. That is the beauty of asymmetric configuration. Okay, having appreciated fly-by-wire, let us look at the technologies wrap up. Sensors and transducers, you will appreciate you need a lot of sensors to make fly-by-wire a reality. Transducers are nothing but whatever is picked up is converted into an electrical signal and converted into a digital signal finally for digital signal processing. You need low loss and low impedance cables. Obviously, you appreciate that we need multi-output power supplies and absolutely robust and fail-proof power supplies because there is no room for failure. And all these are embedded systems and modules. Obviously, we need smart multifunctional display for real-time, state-of-the-art presentation to the pilot in the cockpit. And communication systems, absolutely vibrant. And communication architecture, we will visit this subject later. And obviously, digital signal processing and a lot of capability there. So these are the technologies which go into the fly-by-wire system. Looking at the avionics computers, let me tell you, I want you to appreciate that we don't need supercomputers and state-of-the-art or the latest very powerful computers for this, because the data rate or the decision making or the digital signal processing is limited in its nature. But what we need here is redundancy and reliability. There is no room for failure. There is no room for reboot and cold boot and hot boot, and redundancy has to be absolutely foolproof. There is no watchdog concept. You cannot say, okay, now I have to load a patch, then only the system can work. No room for such things. So that is one difference from conventional electronics. For your quick appreciation, when we started the LCA project way back in the beginning, we got started with the 386 processor for humble functions. Coming to Su-30, the processor used in the mission computers are 486 class, but then we have a number of them. Coming to MiG-27 upgrade, for which is a indigenous effort. Core avionics computers were developed. They were based on 486 processors again. Then Jaguar mission computers are again on 486. And now we have what we call IMA, Integrated Modular Architecture. That means we have a system of systems, meaning multiple computers, power supplies, or multiple functions, a display processor, radar computer, all goes into one single box, but with enough redundancy so that there is no way any function would suffer, though everything is in one single box. And why so many things had to go into a single box, you will appreciate as I discuss further. Coming to some milestones ahead, as far as fly-by-wire system is concerned, I'm sure it will tickle your brains. You have already appreciated that, this is nothing but integration of more or complicated control surfaces. Thanks to fly-by-wire, we are able to handle difficult maneuvers, and we can put difficult and customized control surfaces and still manage the aircraft to behave exactly how you want it to behave. Fly-by-wire. Now, if you take out the wire and use a fiber optic cable, then you can call it fly-by-light, which is already there in the 5th generation and fifth and half generation aircraft, which is under development. You can read up on this on OpenSource. Also, of course, you may not get secrets, but then you can generally appreciate. In your time, these areas will go further, develop further. Neural networks is something which you are already probably studying. Neural networks can come into flying. How? You should be able to fly by thought. If you have the right sensors and a neural network, you wear your neural network helmet on your head, you can sit in the cockpit, you don't have to move anything. You just think of what you want to do, and if the sensor are able to pick it up and interface it correctly with the fly-by-wire system, the aircraft will simply fly. If you watch the movie Avatar, you would appreciate what I'm trying to say. And if you have not watched Avatar movie, please, this is another movie I would like to recommend. Please watch it carefully and think about what I have spoken during my presentation. Neural networks and fly by thought. And in your lifetime, I do not know what all you think things you will do. Probably you will go beyond this, and wish you all the best for that. Having said this, let us come to radars, which stand for radio detection and ranging. I hope you are all okay. I can continuously talk, because if I run out of time, I will skip and jump some topics. Radars at a glance, these pictures will speak for themselves, and these pictures are a repeat of some which I have already covered. Now, one appreciation I want you to have is, okay, these are radars mostly on ground, and they are huge, they are very big. But when it comes to an aircraft, the radar becomes so small. This is a picture of an actual radar on which I have worked, and we call this a fire control radar. And this radar does much more functions than the conventional radars which you see in, this is doing only search. There's also search, but this search, track, and missile guidance radar. So we call it MGR. So he's a 3-in-1 radar. And when it comes to fire control radar, he does much more than that. Let us see this pictorially and appreciate. This is the exploded view of a fire control radar. You can appreciate how compact and tightly packed the electronics is. And it has to sit in the nose cone layout because he has to look forward and scan the space in front of him. It may be as much as 110 degrees or even more. If you use a synthetic aperture radar, you will scan more than 180 degrees. That means you will not only scan the entire hemisphere in front of you, you will even look sideways and a little bit backwards also. And here you can see the names coming up. We will not spend much time on this. You need to have a servo mechanism to steer the antenna, which is inside this red zone. And you have transmitters, obviously, then receiver, then data processors, and finally the data output, which will get further interface to the control and display and further decision-making tools elsewhere in the aircraft. So that is fire control radar, all housed in the small nose cone area of a fighter plane. Modes of operation, I will quickly scan through. You can appreciate that, okay, radars have to essentially scan looking for targets or victims. Then he has to track while scan because he will keep picking up potential victims. He needs to keep a track of its movement, its coordinates in real time while continuing to search his space. Then, depending on the weapon capability of the aircraft, the radar may have to handle single or multiple targets at the same time. We call it STT or MTT, multiple target tracking. And then he has to also sometimes, do a function of terrain avoidance. If the aircraft is flying very low, say treetop, the aircraft should not go and hit the ground. So the radar does give some information to the fly-by-wire system, which can automatically pop up the aircraft, push the aircraft up to avoid collisions. It can, using this radar, you can penetrate fog or bad weather. And low altitude mode, while looking for ground-based targets, so the radar comes handy. You can shoot moving tanks and columns or ammunition dumps using fire control radars. And land mobile is that mode which I'm talking about. You see, the fire control radar does much more or many more functions than conventional radar. Friends, I hope I can pick up speed and continue. This is a typical display that is made available to the pilot. You don't have to worry. The pilot understands in this picture in less than the fraction of a second. That is how he is trained. So he will understand what he has to do looking at these pictures. Some of the radars, technologies which go into radars, when it comes to antenna, you will appreciate that we cannot have a big dish there. We use what is called in inverted Cassegrain antenna. And the latest is active arrays. We have some pictures on that, so we will jump this topic here. It needs to have very powerful receivers, as sensitive as possible. Sensitivity going in the range of minus 110 dBm or even more. That is the kind of sensitivity these radars have. And you need very powerful RF amplifiers, bandpass filters, digital log video amplifiers, discriminators. I'm throwing some technical jargons at you. You may understand some of them instantly, some may not, but by virtue of the notes, you can visit these topics later. Read up, Google up, and if you end up working in these domains, definitely you will learn more on all these things. And you need frequency measurement techniques. More powerful will be the radar. Powerful digital signal processing. The DSP capabilities of radars is required to be much more than that of mission computers and fly-by-wire, because the data rate is much higher here. And of course, you need beautiful transmitters to do its job, because you need to eliminate the target. And the technology that was available in the beginning of history of radars are called magnetrons, klystrons, traveling wave tube, microwave power modules, solid state trans-receive units. I have some pictures as examples. You can see them elsewhere in the presentation. Coming to the cockpit. This is the cockpit of a Mirage 2000 before it was upgraded in India. And this is an upgraded aircraft. You can see that all the dials, electromechanical things have disappeared from the cockpit, and we have just backup compass. Otherwise, everything is now full glass cockpit, all multifunctional display with all the touch controls there all around. And it is much more friendly to fly this aircraft now in the cockpit. So if you are into avionics, you will not only learn, you will learn to maintain, upgrade, and also be probably party to the aircraft upgrades, because the life of the airframe and engine is much more, whereas avionics will witness multiple upgrades in its lifetime. And we in India are very famous for this. Some of the countries which supplied military aircraft to us used to send their delegations to see their aircraft flying in India, because we were still maintaining them, because we managed to upgrade. The MiG-27 is an example. Without the help of the RAC MiG, which is the manufacturer of the aircraft, we upgraded. We did a total avionics upgrade of this aircraft. I was also a member in the team, thanks to my DRDO days. And the MiG-27 outlived its life in India than elsewhere in the world. So that is our Indian capability we should be proud of. Moving on. When it comes to avionics or even elsewhere, when you have a large number of systems, the systems will need to talk to each other. That is where the communication protocols kick in. So RS-422 is probably something which you have studied. RS-232 you must have studied. There is something called ARINC, you already know probably. GOST is a collective communication standards largely used by the Russians. Then MILBUS 1553B is the most common communication protocol the worldwide. And Digibus is the protocol which we have in the Mirage 2000. It is half a generation before MILBUS, and it is also having some secret to it. So it is not easy to crack a Digibus protocol if you want to put something or tap into it. And there are people, aircraft manufacturers or system developers who have their own protocols for their sake of secrecy. So I'm not listing those things here. All I wanted you to appreciate that there are multiple communication protocols, and you are probably going to be in a multi-protocol environment when it comes to avionics. Another architecture I want you to appreciate, if you have a mission computer 1 and a mission computer 2, but you have a common communication protocol, and these are the RTs, systems which we call remote terminals, and typically 1553B can support up to 32 systems on board. That means you can have 32 systems on board an aircraft managed centrally by 2 mission computers in tandem. They are in tandem to ensure that the mission doesn't fail, electronics doesn't fail. Okay, so this is one uniform communication architecture. But if you have systems which belong to different protocols, then we split the architecture in a different way. We have one mission computer handling all the remote terminals which are on a similar common protocol. You have another mission computer handling another generation of protocols, and between them you have a high-speed Ethernet. And if you have still multiple ones, yes, then you need more mission computers or converters. So this is the architecture you will appreciate, and this is an area where some of you would definitely work, especially if you go into embedded systems where you need to learn firmware and a bit of software, or you need to manage the software people who will do the coding for you. So these are all very interesting and very challenging areas and niche technology areas. Okay, we are out of mission avionics right now, and let us come to electronic warfare. And as I understand, I have another 40 minutes to do justice. If required, I'll jump the gun somewhere. This is a picture for me to brag, because one of the systems I served as a project director of have gone into all these aircraft. And it has been professionally a very satisfying journey. And this was also an effort in India to bid goodbye to foreign dependency, because electronics warfare systems are all secret systems. We cannot give visibility to foreigners or other agencies who have clandestine interest in our capabilities and our database. So we have no choice but to have our own electronic warfare systems. And we have been successful. Let me tell you, there are about 800 to 900 systems flying in the country today between Army, Navy, and Air Force. And let me move on. Radars, we have already visited. Now we are going to the other side. If there is an enemy radar and I'm flying in either in friendly territory or enemy territory, I need to know who are the radars looking at me. For that, I have what we call radar warning receiver. We call it RWR. Okay, we wanted an RWR to caution the pilot, look, there is somebody looking at you. Now, having known that okay, there is somebody looking at you, then there was a need to know who is this and what is he doing, what is his capability, positive identification. So we gave this intelligence to the RWR. RWR is able to tell the pilot, look, there is an F-16 in front of you. He has now switched on his radar. Now he has taken up a tracking on you, or now he has launched a missile on you. This much warning the RWR can give. Now, while the pilot is busy doing similar actions against his adversaries, he wanted the RWR to be capable of managing some more of his self-defense systems, maybe managing a jammer or dispensing chaff and flare against the heat-seeking missiles which are coming towards him, and more functions. So what I'm trying to say is the role and function of RWR kept growing with the time. And today, the RWR that we have, I have been party to, is capable of doing all these things. The RWRs are not really, I mean, he's like another electronic friend in the cockpit. He's another brain, another human, superhuman working with him to help him do his functions and also to help him survive the mission and come back safely. So RWRs play a big role. So it's a very, very vital system. So electronic warfare systems actually decide victory or loss in a conflict today, because the wars are going to be electronic in nature currently also, and more so in future. So let me move on to the next slide. This is the cockpit of a MiG-29 in which I had to integrate the system. This is the control and display unit for the pilot. It's a color active LCD. It's switched off now. You can't see anything right now here. And these are the control buttons. So push of a button, this fellow is interactive with the pilot and he's like a buddy in the cockpit. Okay. Now let us see a virtual display of how this is a virtual display, not the actual. See, you can see some symbols popping up. Along with the symbols, there will be some audio tones also, which will be played into his helmet. So audio visual treat is available to him, and pilot is able to make out what is the environment in which he is flying. Which are the weapons looking at him? What is he doing? Has somebody taken a lock on? Has anybody fired a missile? And where is he? Coordinates wise, distance wise, a lot of information is there. And these numbers are to indicate, okay, how many are being indicated. I mean, anyway, let us not spend more time on this because we're running short of time now. And for you to appreciate, for an RWR to function, you have to have the sensor grid all over the aircraft naturally, because the warning can come from any direction. So you need global spherical coverage. So this is a pictorial presentation of for you to appreciate where all the sensors go and sit. When it comes to an AVAX aircraft like the one we have here in this picture, let me tell you, the electronics content is so dense, so huge, so sophisticated. The cost of this aircraft, more than 70% of the cost of this aircraft along with system is electronic in nature. So the aircraft, bare aircraft and the engines put together is, less than 30% of the total cost. That is the kind of electronics and the sophistication therein. And there is something called electronic order of battle, EOB. So you can appreciate that if you have an AVAX aircraft, we have RWR capability. RWR not only does all these jobs, he keeps recording the parameters also. So there is a lot of data that comes in. So if all this data is chewed in real time, in peacetime and wartime, we get what is called the electronic order of battle. That means in the area of interest, whether inside our territory or for enemy territory, what are the sensors, where are the weapons, where are the aircraft, what is happening there, we have real-time update. And that is called electronic order of battle, EOB. And EOB is very important, vital for our existence, and the currency of EOB and accuracy of EOB is the decider in electronic battle. So I wanted you to be familiar with this term EOB. And coming to what is called MANPADS, Man Portable Air Defense System is called MANPADS. In the history of peacetime and wartime, probably maximum number of aircraft have been lost to this, what is called MANPADS. Here is pictorially explained. And these are highly agile, very easy to handle. They typically have a kill range of 3 to 5 kilometers. So obviously it cannot shoot an aircraft which is flying very high, but the aircraft coming for landing or coming low for attack, they all can be handled. US Air Force lost majority of its aircraft to anti-aircraft shoulder-fired missiles in the Vietnam War. Here is a Viet Cong who is waiting with a Stinger missile system for an aircraft. This is the picture. So there are some figures shown to indicate the airspace of effectiveness when it comes to MANPADS. And these also have electronics on board, we will see. Okay, let me say one more thing. These sensors can be infrared or ultraviolet. Please remember these terms, infrared and ultraviolet. We will visit what is this. And this is a typical pictorial presentation of how the engagement takes place. The sensors on the missile itself picks up a source of heat or signature of an aircraft. It gives an ear tone to the launcher. The man who is firing, he gets a tone in his headset to say that, look, I have taken a lock on. He can slew the seeker of the missile to a target which he has picked up, and he can make the missile lock, and the missile says, okay, I have picked up and I have a lock, and I'm ready to go. He just has to press the trigger and the missile goes. And it's a fire and forget system. And in this picture, you can see the aircraft has dispensed what is called flare. Flares are heat sources which have got thermal, infrared, or UV signatures stronger than the aircraft, and the missile is misguided onto the flare while the aircraft is escaping from here. This is a typical engagement scenario. And this is another picture of flares being fired when there is a threat picked up by the missile warning system telling the pilot, look, there is a missile coming towards you. This is how laser beam rider threat can be. This is land-based, obviously, and here have a laser-assisted aiming system. You can use this to aim at an advancing tank or an AFV, armored fighting vehicle, or a column. And when the victim comes within the kill range, you just press the trigger and the missile goes from this canister. So beam rider is the guidance principle used. That's why it's written here. And whatever I have told you is there listed here: launch platform, tracking system, missile in a launch container, all well dug in and very difficult to detect visually in a war scenario. Now let us appreciate all the necessities in EW capability. RWR you already know because I have already explained to you. Then since there are missile threats, we need missile approach warning system. We call it MAWS or MWS. Then since laser is used by the weapon system, we need a laser warner on the aircraft. And we need jammers to make these systems ineffective. We call them SPJ, self-protection, especially when you enter an airspace which is heavily defended, say Air Force Station Chaklala in Pakistan or Kahuta nuclear complex in Pakistan. Each and every aircraft has to protect itself by using what is called an SPJ. And in a formation of aircraft, there is an escort jammer who basically gives escort jammer cover. The jammer is much more powerful than the SPJs, and he gives particularly the cover during the cruise journey. And once the weapon delivery area, the aircraft enters, the escort jammer duty is over. Anyway, let me not get into more details because we don't have the time. And there's something called standoff jammer. He doesn't enter the kill zone of terminally defended system, the area. He stays off but gives jammer coverage. These are typically based on transport aircraft because you need to pump huge power. And CMDS, countermeasure dispensing system, is already familiar to you. I have already spoken. There is something called directed energy countermeasures. If you have a laser source or a weapon aiming source you have picked up, you can make it ineffective by pumping huge energy onto that sensor so that the sensor gets saturated. It's called EMP, EM power, electromagnetic power. It's like EM bomb. Coming to unification of EW suits, you have seen that depending on the role of the aircraft, you need to have all these systems on board. And where is the place, where is the power, where is the space for all these systems to be put? So to tide over this problem, we try and unify these suits. So we have unified suits today. That is the trend of the time. For all the warner grids, we have a single system called multispectral warner, which does the radar warning job, missile warning job, laser warning job. Everything is rolled into one single sensor system. And then we have electronic attack system, which does all the jammer duties and also the DCM duties. And then for electronic protection of the aircraft, we have the CMDS. And a typical unified EW suit will do all these functions. So that means it is a system of systems. And I hope you are not saturated. So now let us come to a different approach. Having understood the scope of functions, what the electronic systems have to do, let us look at the requirements of battle electronics. B stands for battle electronics. Unlike what we have in the rooms or in a huge building, your office complex or airports, or even a static installation like a space center, the electronic systems employed in military applications need to be rugged physically because the conditions in which they have to operate are different. You have to operate on mountainous terrain, rugged terrains, maybe amphibious operations. You have to go into water, come out and function. So they need to be rugged. They need to be absolutely compact as possible because space is at a premium. Even in warships, in submarines, there is no extra space. So every square inch, cubic inch matters, and the degree of ruggedization matters. Weight and volume matters because every kilo matters when you have to float the ship or you have to fly the ship. And the degree of vibration levels are very, very high. So they need to be proof to all these physical phenomenon. Coming to the electrical side, they need to draw minimum power and against as much efficiency as possible. So they need to be very efficient electrically and with a minimum consumption of power. Needless to say that their thermal efficiency should be very good. Otherwise, the cooling load, the heat load is going to be much more higher. So the cooling requirements should be minimum. But there is nothing which does not heat up. So there will be cooling systems on board. So those cooling systems have to be very, very efficient. They are also electronics by themselves. Coming to the environmental requirements, depending on where your systems are employed, you need to be having a resistance or resilience to salt and foggy weather. All naval systems have to have resistance to salty conditions. Some systems need to be rainproof. They should have fluid contamination proof against the hydraulics which may leak into it, or some acidic rain that may happen in some part of the country. So all these are environmental specifications. Coming to the environmental other specifications in terms of temperature and pressure, there is something called ISA, International Standard Atmosphere. So knowing the conditions in which our systems have to operate. And one more point I would like to tell you is that there is some typicality for Indian forces. We have the highest battlefield of Siachen and all this Kargil and Pangong So Lake, which we have seen the picture of. They are at such altitudes where we have to fight a war, and many of these other countries in the world don't have such battlefields. So our requirements become much more stringent. This is a picture taken from my favorite book of Basic Aerodynamics, Flight Without Formulae by Kermode. And I wanted to explain international standard atmosphere for your easy appreciation. Here we have Mount Everest at 28,000 feet. And at 28,000 feet, the temperature is already minus 40. At 30,000 feet, temperature is minus 45. And a little above 36,000 feet, temperature has hit minus 57 degrees. And then the temperature remains static. Whether you go to 50,000 feet, 60,000 feet, 70,000 feet, into the space, temperature remains minus 57. So all our military avionics have to be capable of functioning at temperatures as low as minus 57 degrees centigrade. When it comes to army systems, land-based systems, since we have to operate at Siachen Glacier, where the temperature can go down to minus 25 to minus 40, because on the foothills of Mount Everest, the temperature can touch minus 40. So we don't want any system or a radio refusing to wake up because temperature is minus 40. It has to come on when we switch on. The batteries should function, the generators should come on. So that is the kind of systems that we have. So military avionics, military electronics by and large must meet the ISA specifications, this I wanted to say. And also they should not explode because the air is going to be thinner and thinner. The pressure outside is going to be lesser and lesser. They should not explode because of low pressure, because they tend to expand. That is another requirement. Okay, so these were our requirements. Now let us come down to the technologies per se. This is for the tech savvy people. Some of these terms which I'm going to speak, maybe you're going to listen for the first time, but you can re-register them through the notes I will supply and revisit them. But most of them will either register or they will be appetizing for you. I promise you, let us visit. This is one slide which I'll send to you. Please keep it for posterity. As long as you are an engineer, electromagnetic spectrum, you will keep referring to this. Now let us spend 1 or 2 minutes on this. Let us start from 30 hertz to 3 megahertz. This is called the radio waves. Okay. And the frequency of military interest starts somewhere at 1.5 megahertz. 3 megahertz is here. So there is a marker here. Okay. The frequency range below that is being given for, infotainment, all your FM radio, AM radio, and the ham radio and all is in that. But when you hit 1.5 megahertz, or actually even 1 megahertz onwards, it is of military zone. So the use of electromagnetic spectrum in the military zone has to be with proper permission, license, or it will be taken as breach of and it is punishable by Act. Okay, so high frequency starts at 1.5, then 3 megahertz, all the way up to 30 megahertz is known as HF, high frequency. We will hereafter, I'll say the word HF. From 30 to certain frequencies around 88 to 108 is called VHF. Okay, then UHF starts from there all the way up to, like in UHF actually goes up to just before 1 giga. After that, it is L band in the other parlance. But for your broad understanding, let us say, okay, up to 1 gigahertz is, so 3 to 30 is HF, 30 to 300 is VHF, 300 to 1 giga is UHF. For thumb rule remembrance, I want to say. Above that, frequency is called microwaves. You have already visited. Okay, microwave starts from 1, particularly from 3, and it goes all the way up to 300 gigahertz. Then we have the infrared range. Then we have the visible light. What you are using, your eyes are using, is this frequency. White light is in that. And still above that is the UV, ultraviolet rays. Then we have the X-rays, then the gamma rays. This is the EM spectrum. So all these warfare, whether you use HF systems, VHF system, UHF systems, infrared, UV, or even X-ray, there are X-ray radars for seeing behind the wall. When you want to enter a building and if you want to see what is the activity behind, there are, radars which are proximity radars. So to say differently, all these systems, their development, their progress, their employment is nothing but exploitation of the EM spectrum. And this spectrum is very highly regulated. And it is monitored, it is policed, it is breached and caught, and all the rogue actions happen here. I will just say that much and leave it at, okay, please remember EM spectrum for life as long as you are an engineer. Okay, having said that, let us come to the radios at a glance. I already mentioned that, okay, 2 to 30 is the actual exploitation of HF radio in our domain. You can see some pictures of HF radios. By virtue of their lower segment, the data rate that can be handled by HF radios are limited, and by phenomenon, they are the over-the-horizon radios. That means if you have a very powerful HF radio, you transmit, your speech can travel around the world and come back to you because of the troposcatter phenomenon. But when you come to VHF range, that does not happen. Say 30 to 88 typically, it is line of sight. It is not over the horizon. The curvature of Earth, which is known as 1/60 principle, that means if you have a 1 kilometer height antenna, from a 60 kilometer at 1 degree, you can see the antenna. But you cannot see anything lower than that because of by virtue of curvature of Earth. This is called 1/60 principle. That means if you are looking at 1 degree up, at a 60 kilometers, you can see a 1 kilometer tower. That is what it means. So that is a line of sight. So there is a huge limitation when you use VHF. Anything beyond line of sight, you may not have radio contact. But the data that can be handled, the bandwidth is much more because your frequency is higher. Coming to VHF radio, it is typically from 108 to 156 and then 225 to 400 megahertz. And they are also line of sight, not over the horizon. It can support higher data rate. We have UHF radio, like this handheld radio shown in the picture is a UHF radio, which is used by commandos. And also some walkie-talkies you see, they are using the lower side of UHF. Some of those are in this 225 range, not in this range. This is exclusively for military application. Limited range, maybe 3 to 5 kilometers, but you can pass audio and video. Some pictures also using the UHF radio. Okay, this was radios at a glance. And UHF radios are for handheld operations. Coming to some radio issues you should be familiar with as an engineer. You have already studied the waveforms like amplitude modulation, frequency modulation, and a host of modulation techniques. You have also probably studied the keys and codings. Let me not get into the details because you are more familiar than with me, more current probably. The problem starts when the number of radios have to interoperate. If I have an FM radio, only an FM radio can work with me. I have interoperability problems. And you have already seen that, okay, some radios will have only line of sight contact, some have OTH, over the horizon. So if I want to use the entire spectrum for obvious reasons, operational reasons, I need to have all those radios on board an aircraft or the system or a platform like ship or tank. HF for long range communication, VHF for short range communication with my buddies and friends. I need UHF capability if I have to speak from ground to an aircraft and vice versa. Aircraft has to speak to ground. And so number of radios means that much more space required, interoperability issues, EMI, EMC, electromagnetic interference between these two, because there are other issues. And then coming to applications, for each radio you need to have an application, you need the bandwidth. All these are problems. So the need to address military issues have led to findings and progresses. So we have migrated from legacy radios to what is known as software radios, software control radios, to what is now known as software defined radios. Software defined radios are digital radios, legacy radios can be analog. Now software defined radio addresses all the communication problems, and this is the future. And in your young time, in the times to come, the next 10 to 15 years, the requirement of software defined radio in the country for military, paramilitary, state police, NDMA, and all put together, and other agencies put together, is mind boggling. It is in lakhs. So I'm sure a lot of you will end up working in software defined radio. And so SDR can be a separate topic or area of specialization. And just to revisit the bands, a single HF, single SDR can handle the full band. And software defined radio will be interoperable. That means if I have an SDR with all the waveforms preloaded, I can talk to all the legacy radios, analog radios, and I can talk in any band and in any waveform. And I can switch waveform from, if I want to speak to Navy in secret, I will use a waveform which is shared between only me and Navy. And if I want to switch to an Air Force contact, I will switch to another waveform while Navy cannot listen to that, and vice versa. Just to explain the situation I was telling you. So we can maintain secrecy. One single radio can behave as if you have got multiple radios with you. So all radio issues are addressed by SDR. Obviously, we need a waveform bank. We will see a little more of this as we move forward. Just to, I think RWR revolution, I will just jump a little. When the RWR started, we only had an LED indication, giving an LED indicating, lighting up to say that there is a threat in this particular direction. Today, RWRs talk to the pilot. It has got synthetic audio. It will tell the pilot F-16 at 40 kilometers at so-and-so bearing. He has taken a lock, he has fired. M13, whatever. So like that. Okay, that is RWR revolution. Technology areas for your satisfaction. Okay, this is a host of antennas all put together in one single picture. These are the products coming from a small company housed in Cochin. It's called Verdant by name. I am associated with Verdant. Verdant designs, develops, and manufactures and supplies these antennas all over the world. And that is one picture I wanted to put. We use super components for the technology areas' sake, PCB technology, signal processing, technique generation, receivers, transmitters, antennae. These are the areas where specialization is called for to be employed in military avionics. Coming to super component, I will run through some names for you to register. The notes will help you further. There's something called MMIC, monolithic microwave integrated circuits. microwave power modules, multi-octave RF front ends, multi-octave up-down converters, fast synthesizers. Thanks to surface-mounted devices, multi-layer PCBs, printed circuit boards are the order of the day, and the number is growing by the day. And my system in which I worked, I had 24 layers in my system, and now the number of layers in systems are 48 and beyond, depending on the degree of packing. And EW systems are essentially embedded systems. So is the case with most of the avionics. They are embedded systems, so they are system of systems. Some are living systems, meaning they are programmable and has artificial intelligence in them. So they are like almost another friend in the cockpit. And the capability of digital signal processing, we talk about millions of pulses per second these days, and the number is growing by the day. It is firmware intensive and software intensive. The systems which I managed had, depending on the application, had 50 to over 1 lakh lines of codes in the software. So such is the volume of software. Receiver technologies, analog receiver front ends, where sensitivity and bandwidth was a huge concern and worry, an area of research. Electromagnetic interference and compatibility were challenges. Frequency counting techniques came in, and IFM, DIFM, digital instantaneous frequency measurement techniques. And there are some frequency techniques which are IP protected. Digital receivers are the order of the day. So from analog receivers, we have migrated to digital receivers. So like SDRs, digital receivers have much more capability. I have a few more slides on digital receiver, which I am forced to skip because I am going to run out of time. I just want you to remember these terms: instantaneous wideband receiver. When I send you notes, I will send you the full form, don't worry. And narrowband receivers. So if you end up in digital receivers for electronic warfare, you will specialize in these aspects. The latest is channelized receivers. And these are some pictures for your visual treat. And digital receivers will overcome all the limitations of analog receivers. I just want you to appreciate that there is something called digital RF memory. This is a very powerful tool which has come into jammer capabilities. For you to jam, you must have experienced mobile jamming when you enter high security zones. Suddenly your mobile doesn't work because you have been jammed. Then there's a VVIP movement happening, President, Prime Minister going past, your mobile stop working. That is because of jammers. Now in electronic warfare, for me to jam somebody, a radar or something, I need to essentially capture his signature, radar signature, store it, analyze it, tinker with it, and throw it back onto him. That is when radar jamming happens. So initially we used to use what is called FML, frequency in memory loop. There were electrical delay lines. It had typical limitation of, I could not hold a radar signature for more than 70 nanoseconds, and a pulse for not for more than 5 to 6 microseconds. So only some techniques I could employ. Now I have digital RF memories with unlimited storage and numerous possibilities, and that is some area of specialization. Again, coming to transmitters, the world started with discrete transmitters, which looked something like this. We had components and wires connecting the components, all shabby, jumpy, and in case of a snag, we had to spend days and months to crack the snag. With advancement in technology, this is a picture of an MPM. From discrete to MPM, it has been a huge journey. Let us look at some pictures. Magnetron to TWT based. These devices needed extra high tension. That means higher voltages. There were duties, limitations in duty cycle, power supply issues, and fidelity. Journey through transmitters in pictures. This is a picture of a magnetron. This is a picture of a klystron. Magnetron was the first, then came klystrons, then came traveling wave tubes. In sizes, this is the biggest, this is smaller, and as technology advanced, they became smaller and lighter for your visual appreciation. This is a microwave power module. This is a mini TWT and SSPS. Sorry, this is an SSPS, solid state power amplifier. And the latest technology is solid state trans receiver units. This is a 1 kilowatt solid state trans-receive units which I have used, and see how compact it is. You will see in another picture how it doesn't have any high tension, no high voltages, no voltage issues, low power combiners, no power combiners. The technology used is gallium arsenide, gallium nitride, and research is going on silicon carbide now. These are some areas where some of you will definitely work. These are some of the advantages. They will never fail because it's a bank of power TR modules. Even if one module fails, it doesn't fail the entire transmitter. Others will continue to work because power combining happens in the air. There is no combiner. So some solid advantages there. These are the types of antennae you will specialize in. These are the design figures. They are not the finished products. Spiral, sinuous, Vivaldi, horn. You will learn them. This is a collective picture. This picture also I'll put in the notes so you can enjoy these pictures later. These are Vivaldi antennas in stack. These are the latest antenna array techniques we use in EW systems. This is a 1 kilowatt transmitter with electronic steering capability, and you see how small it is. This is a pen kept there. It is just twice the length of a pen and so compact. Typical user-friendly thing for military applications. This is a schematic I will skip. This is another live picture of a active array jammer things. We will spend 5 minutes on a couple of things before we conclude. These are very important for you. Since the requirements are very stringent, we also need to have regulatory standards in the country and worldwide, because we are in an international scenario. We have bought-out systems, we have co-produced systems, we have indigenous systems which have to communicate with imported systems. Anything that is to be put on a military aircraft has to meet the MIL standard, military standards. There is a host of standards. So what we generally currently follow is the MIL standard 810, E, F, and G for avionics. You will get familiar when you are employed in this domain. There is something called MIL standard 461C for EMI, EMC control. STANAG is a standard which is a short form for Standard NATO Agreement. This is an agreement and standard between all the NATO countries for unified standards and codes so that their systems can interoperate. JSS Penta F5 is an Indian standard, environmental standards we follow. SCA is an American standard which was floated by the Americans for management of software-defined radio. Otherwise, the SDRs will not talk to each other. When it comes to in India, we will have an Indian standard. It will be an SCA plus an Indian standard. There is a policy formulation happening. I was a member of the policy formulation committee till I retired. And the SDR development in India will happen, or the SDRs employed in India will conform to the Indian standards. It is something like the pollution standard Bharat stage 6. So we'll have our own standards because we don't want to be subservient to SCA, because if we follow SCA, we will be exposing some of our capabilities to others who may have clandestine interest. So we'll have our own national policies. IEEE standard is something I don't want to talk about because you're all IEEE people. There is something called Radio Technical Commission for Aeronautics, RTCA. So the radios which are put on military aircraft will meet DO standards for its EW systems. All the EW systems, current and future, will conform to DO 178B or C, depending on the criticality of the software. DO 256 is what the hardwares will have to conform to. These are all volumes of books by themselves, but you will get involved in this when you are employed there. And since there are standards, there are also standards for the components. All the components need to be MIL standard. And in case you don't get a component for a particular application, we pick up commercially off-the-shelf COTS products, but they are screened through MIL standards, so we call them COTS MIL. That means commercially off-the-shelf products which are screened and qualified for military applications, COTS MIL. Then we have industrial standard components for all other non-critical employment in the military domain. If you have a control room, okay, you can have an industrial standard system. Only thing, you will have a standby system to avoid redundancy problems in case of failures. And you can see some pictures of components and MIL grade handheld devices, and also the cable harness which go into military aircraft. They are all MIL standard. And coming to the regulatory bodies in India, we have what we call CEMILAC, Center for Military Airworthiness and Certification. So anything that flies in the country is CEMILAC approved, especially the ones developed here. Bought out systems also undergoes the CEMILAC scrutiny. And CEMILAC, for discharging its duties, have regional centers for military airworthiness, RCMAs, regional centers all over the country, having regional responsibilities for the military aircraft or air systems operating in that area. So CEMILAC is like the Supreme Court, stationed at Bangalore. RCMAs are like high courts for regional coverage. So anything that has to be put on these aircraft have to be qualified by these people. And for production, we have quality assurance agencies. So we have a DG QA for the Army. It's a vertical organization. It's commanded by a Lieutenant General. And we have Army presence, QA presence, wherever there is military production happening. Even in the industries which are supporting the Army production, there are people giving QA coverage for production. So everything that is brought into the inventory of the Army is qualified and certified. We have DGQA for naval organization is a little different. They have multiple verticals. They have a separate DQA for warships, for naval stores and armament inspection. And when it comes to Air Force products, we have DGAQA, Director General Airborne Aeronautical Quality Assurance. DGQA is the Director General Quality Assurance for Army. And coming to defense public sector undertakings like Hindustan Aeronautics Limited, Bharat Electronics, we have CRIs who are representatives of these QA agencies on the station where production happens. And then if there is an industry like the one I talked about, Verdant in Cochin, is given production quality assurance coverage by representative of the customer. So if we are exporting, we give a COC, Certificate of Conformance, that is self-certification. And in case the customer is in the country, Army, Navy, or Air Force, then they have the representative witnessing our qualified, the production tests, critical tests. So that is about the regulatory mechanism in the country. The road ahead, defense public sector undertakings were the norm when post-independence journey started, because nobody else had the financial muscle to start until the Tatas and Birlas came into the scene, and then industrial revolution picked up. They were largely known as the corporates. Now we have more corporates. We have Mahindras and Adanis and more people, Ambanis and many more in the corporate world. Some of them are having verticals in the defense sector, and remaining are in other sectors. Then came the era of joint ventures. Then by national policies, the defense procurement policy and defense procurement manuals stipulated that there has to be offset programs for us to permit import. Certain percentage of the product has to be co-produced in India. The payment will be in Indian money. So offset programs started. Then we instituted protective policies for MSMEs, medium, small, and micro enterprises. And we need more and more MSMEs coming in the days to come. Some of you can directly go and start the SMEs. All of you don't have to look for employment. You can become employers and entrepreneurs yourself, because the policies are now much more conducive. What we generally call is PPP, public-private participation. And there are maintenance and repair and overall centers opening up in India. A lot of leading big brands want to set up shops in India because India is a cheap destination for manufacturing as well as HR, human resource. Airbus and Boeing, they all have MRO centers coming up in some parts of the country, Nagpur, Hyderabad, etc. And a lot more manufacturing hubs are going to come up thanks to the policies and changes. The Indian advantage is already known to you. We have an advantage in terms of average age of human resource available, and India is cheaper for manufacturing vis-a-vis many other countries. So we have the Indian advantage, and the Chinese probably have an edge over us. Yeah, we definitely have advantage. This is my last working slide for discussion. Conclusion, I think I've more or less been able to rush through. In conclusion, to my lovely audience, I would like to say that battlefield electronics is an absolutely engrossing, interesting, very satisfying area. 33 years of my life in uniform, I have enjoyed every day of my service, and particularly the 10 years when I was on deputation to DRDO. It was sheer fun, nostalgia, and good fun. Okay, so let me tell you, wind up by saying that, okay, military avionics or battlefield avionics, electronics is as fascinating as challenging. And it is technology intensive. You got a feel of it by virtue of what I covered, and it was only tip of the iceberg I covered. Because if you give me 1 week, I can bore you, I can torture you to death, jam you with more information. And it is absolutely knowledge intensive, because where this is an area where we only have rolling stones, no static stones, no gathering of moss. There is perpetual motion, and it is the most dynamic electronics industry among the other industries in the electronics domain. And if you are in this domain, you can remain a student your lifetime. Look at me at the age of 50, I'm running 59, and I am growingly aware of how little I know when it comes to battlefield electronics. So you can remain a lifetime student. It will keep you young and dynamic. And in the days to come, in your time, when I will be history and you will be holding the baton and carrying the mantle, there is going to be exponential growth in our country. And I'm very proud and happy to say and see that. And so, friends, brace yourself for the journey, and not to worry. If you are vigilant, if you're alert, if you have an eye for details, and if you're focused, you can even befriend a tiger. And battlefield electronics is no tiger. Wish you happy landings in life, and thank you for listening to me.